generation of gravitational waves in the context of a random source coming from the early universe, and okay, we cannot do it in full generality, but we can study two cases, fast source and continuous source. Okay, so let's now focus on the fast source. Okay, so we again take this time interval eta final minus eta initial in the radiation dominated era. And the typical example for this kind of sources are first order phase transitions. We will see later on what it is. And in this particular context, as I said, what we expect is a peaked spectrum for this particular source, for the signal of this particular source. Okay, so we have already seen that once the source is gone, okay, so after time eta final, we just have freely propagating plane waves with coefficients that get actually depend actually on how the source has acted on time during this time interval. And now, basically, you want to calculate the power spectrum, okay, so the two-point function today at theta 0, and this we have already seen, this formula I showed you this morning, okay, so for modes that are well inside the horizon today, of course these are the only modes we can actually measure today, that's what you get, okay, so you get that you cross-correlate the amplitudes. Now, of course, you would like to express this in terms of the gravitational wave energy density spectrum per logarithmic unit of frequency. As I showed you this morning, you get this factor k squared that comes from the fact that you need to do one-time derivative, and when you do one-time derivative here, you just get a k. Okay, and then you see you cross-correlate this quantity, which means that if you go back to what it is, you have a double time integral. Okay, you have a double time integral because you have this times its Fourier conjugate, and of course this means that you take this pi r once at time t, and the other integral is at another time with a complex conjugate. Okay, and so that's why you actually need an equal time correlator of the anisotropic stress. That's what enters in the energy density. Okay, so you get twice a time integral. This is the Green function that you compose with the Green's function of the two time integrals that depends then on a time difference, and then you have this, so the unequal time correlator. So that's the quantity you want to know when you actually want to find a gravitational signal from the early universe. And this quantity is in general very difficult to find. So for many sources you need to have numerical simulations to find this quantity. But here, with this assumption of a fast stochastic source, we can try to see how this thing looks like doing some, obviously, assumptions. So the first assumption is, now this time interval is much smaller than the Hubble time at the moment of the generation. Okay, that's what I mean when I say a fast source, so much shorter than one Hubble time. Okay, and therefore there is no evolution of the scale factor, and this you can then fix it to your particular time star at which the source is operating. Then you can also say, okay, I'm interested now in modes that are not only they are inside the horizon today, but let's say that they are outside the horizon at the moment in which the source is operating, okay, just to simplify matters. And therefore this product is much smaller than 1, which means that this cosinus is almost 1. And then you can also say, okay, let's try to suppose that this thing now does not depend on time. Okay, we take it constant over this time of action of this particular source. We suppose it instantaneously turns on, then it's constant, and then it instantaneously turns off at theta final. And so with this kind of simplification, you actually end up So for this range of modes, yeah, with this expression here that you can easily rederive from here. So basically, you see these 2 times integrals, they just give you a delta eta, so the time integral eta final minus eta initial, delta eta squared. And you can multiply it by h squared, h at the generation time. You then basically get this quantity here is how much energy is available in the source, so how much energy density you have in the anisotropic stress with respect to the energy density that is in the universe at the moment of the source operation. Okay, so this is somehow tells you, what is available there to source the gravitational wave. So it's a clever way to put it, and then because you divide by rho radiation, then you need to multiply by rho radiation, and that's why in the end you get this particular factor, which is the radiation parameter today. And then, of course, so this comes from here, so the 2-point function of the source of the anisotropic stress. It is going to have, of course, this quantity, okay? This is basically the amplitude of the generation process. And then, of course, you will have some kind of power spectrum of the generation process. I remind you that we are in the case of a random source as well. So that's the only thing we can know is the anisotropic stress power spectral density. And so it will have some kind of frequency dependence or wave number dependence. Okay, this is just to get the dimension correct. Now let's try to count here. So what do we want to detect? Here, this to be detectable, for example, by pulsar timing arrays, this should be of the order of 10 to the minus 9. To be detectable by GLISA can be a bit smaller, 10 to the minus 11. This factor here is just the energy density in the universe today, is of the order of 10 to the minus 6. Okay. This is the ratio of the relativistic degrees of freedom, is something of order 1 for what we are interested in. And therefore, you see that if you want to get 10 to the minus 9 in this case, okay, when this amplitude is 10 to the minus 6, you basically need these 2 quantities, which are really what counts, so how fast is your source and how much energy it contains, they must be at least 10 to the minus 3. In the case of LISA, they can be this product of these 2 terms, all this is sort of order 1, can be down to 10 to the minus 5 because we have 2 order of magnitudes more of sensitivity. So what does it mean? Now, I remind you that this is anisotropic stress, okay, with respect to radiation energy density in the universe. The CMB is telling you that this guy basically is at a level of 10 to the minus 5. This is the usual anisotropy that you measure in the universe, which you know is small. But the point is that here we have a fast process. So this guy can be large on a very short time and on scales that are actually not probed by the CMB. So you can still have sources, interesting sources, but of course they need to have quite a lot of energy in anisotropic stress with respect to all the energy that is in the universe at that particular moment. Okay, so to get something detectable, you need a very anisotropic process, and that's not easy to get. Yes?
Do you maybe have an example of such a source?
We will have, yes. I hope we get there. Okay, and also you need slow processes in the sense that the closer this thing is to 1, the better it is. Okay, so this thing here, by assumption, because we are with a fast source is smaller than 1, okay, but of course it enters squared in the amplitude, so you actually want this to be, as long as possible. So the point is that only slow and very anisotropic processes have the chance to generate detectable signals for subbubble sources. Okay, so you need a lot of energy on the longest time possible with respect to the Hubble time to get something observable. Now let's concentrate on this part here. So this is now the power spectrum, and this now is a characteristic of what I told you before, right? So we can assume that this source has some characteristic size. And we have seen it already, is this L star, okay? So the process is operating with a characteristic size. And the process cannot be correlated on scales larger than this characteristic size, because here we are operating, here everything is causal and everything is fast. So this power spectrum is going to be just white noise, so uncorrelated process at wave numbers that are smaller than 1 over L star. Okay, so that's where here is just flat in K. And then, of course, once you get to wave numbers smaller than 1 over L star, so you get to scales that are smaller than this characteristic scale of a process, you can have some slope that depends on the source detail. Okay, so that's exactly the same relation that we have seen before. Okay, and so if you now put this into here, okay, and you account for this term here, which is there to keep the dimension correct, what you get is that for this kind of scales, so that are inside the horizon today, but outside the horizon at the moment of the generation, and of course at the moment, depending on also on this scale L star, you get a characteristic increase of the gravitational wave power spectrum as K cube. You probably have seen it in papers. It's something that is extremely general. Okay, whenever you have a causal source in the early universe, okay, a peaked spectrum, the part at low wave number increases like K cube. And here we see how actually you get it. Okay, so this is maybe a bit complicated, so I just skip it and I can come back to this if there is time. But basically, this is an example of a particular spectrum of the general features of a gravitational wave spectrum from a fast source. So here we have omega again as a function of wave number, okay, normalized with the Hubble scale at the generation process. And here you see, this is the range of validity of the simple solution that I found, and it does increase like K cubed. This is extremely general behavior, okay, because of these causal properties of the source. Then you will have in general a peak, as I told you, fast processes generate peaked signal, and this peak is in general at 1 over the characteristic scale of the anisotropic stress. So this peak is simply inherited, so the white noise region transfers to the K cube, while the peak is given by this K of 1 over L star. Okay, so this spectral shape is inherited by the shape of the anisotropic stresses. Okay, and then you have some slope here that really depend on the detail of the source. So then there is this particular region here that can change between the Hubble scale and 1 over L star. But sometimes this L star coincides with the Hubble scale. So this region can be there or not, it depends. But the important part is this K cube and this peaked structure typical of fast sources. And now let's see the other case, the case of continuous sources. Okay, and here, so before the typical example were phase transitions, now the typical example are topological defects. Okay, so now we suppose that the source is operating continuously in the radiation-dominated era. So there is no this delta eta parameter, which is the source duration. So, of course, you do no matching at the end time of the source, because there is no end time of the source, okay? And so there is no free sub-Hubble mode solution as well, okay? The source here is continuously operating. So you never have freely propagating waves. So your solution now, again, in terms of this big H quantity, just normalize with the scale factor, from the green function, from the green method, you get the green function here, the integral in time of the source from the initial time when these typical topological defects form up to the time you're interested in. Okay, once again, you do the same thing. So, okay, of course, from this you can derive HR prime. So you divide by A, and then you derive by time, okay? That gives you this sinus becomes a cosinus. The term in which you derive the upper boundary goes to 0, because you put the same time here, so the sinus is 0. Okay, so you know what is the solution, and then you insert it into here, again, as we did already. Then the energy density is proportional to this guy. Now, you will notice here there is no more a k squared h. So before I could say that, yeah, there it is. Because we have freely propagating subbubble modes, the time derivative of hc is just k squared hc, okay? But now, instead, the time derivative is just the time derivative. So we cannot put this k squared term because there is no freely propagating subbubble mode. Okay. So in the end, if you can try this exercise, you put this into here, that's what you get. So this, once again, this average operates only on the only random part of this is the pi, okay? So maybe this I forgot to tell you before. So of course, here is exactly the same thing. You know, the average operates on the only random part of these coefficients, and the only, oh God, where am I? Okay, the only random part of this coefficient is this one. This is not random, okay? So that's why you get the unequal time correlator. Here is exactly the same. Okay, so you get the unequal time correlator, you get the Green function, and you get this double time integral. Of course, the difference now is that here there is no longer any eta final. Okay. Now let's see what can we say about this guy. So before we did some manipulation of this complicated integral, assuming that the source was short. Focusing only on super horizon modes at the moment of the generation, so k eta in much smaller than 1. So we did these simplifications. Here there is not much we can do, unfortunately, in full generality. So what we can do is basically to focus on this particular case of topological defects, okay? And in this particular case, indeed, this unequal time correlator has a particular form. And, you know, indeed, I'm taking this from the topological defect case, but in reality, it is something that is fairly general for these long sources. We can have cosmic strings, for example. We can have a Kibble mechanism with a scalar field, etc. It is a fairly general form for this unequal time correlator. Okay, and what are the properties here? So the properties are scaling. This is a property of the topological defect networks. It simply means basically that, these quantities here, at some point, they behave like the background energy density in the universe. The other thing is that it decays very fast in the off-diagonal. So this is basically a quantity that is concentrated when tau is equal to zeta, and when tau is different than zeta, there is just a fast decay. Okay, and when tau is equal to zeta, it actually decays as a power law. Okay. So now let's put, and V square, V to the fourth, this is the energy density of the topological defect network. So it's basically the energy scale of the phase transition that is generating the topological defects. Okay, and now if we substitute this quantity into here, what you get, and you focus again on the energy density, okay, so here I have changed the variable just to show you that we can get rid of, time. So now x is just k times tau is x1 and k times zeta is x2, okay? Because here I can simply rewrite everything in terms of k times time. That's also what appears in the green function. And now you see, now this integral, you really don't care much what is inside here, in the sense that the moment in which this guy is decaying as a power law, which is what we said, okay, you see that this integral becomes more and more independent on the upper bound. Okay, so you are integrating a function that is decaying in time. So at the beginning, of course, you add up, but at some point it is decaying more and more, and so at some point it is no longer important up to which time you calculate it. And that's indeed what is giving you this flat spectrum. Okay, so basically, because this thing is progressively independent on the upper bound of integration, you don't care really up to when you are calculating this energy density, because at some time it stabilizes. And it stabilizes then to a constant solution. Okay, so this quantity here is just a number, and it is just this dimensionless integral here that will give you some sort of amplitude, okay, of the signal. And so this is what happens with typically with a long source in the radiation era. So forget about this part, this is the matter one, and here different things are going on. But in the radiation era, you just get a flat spectrum over frequency. Okay, so that's the general solution in the case of a continuous stochastic source. Okay, so this ends what we can say more or less generally on this spectra. Okay. Yeah, I don't know if you have questions up to here, please.
What is x?
X was k times eta, I told you, right?
Okay.
So the point is that I want to make this integral here dimensionless. Okay, so it becomes something that is disconnected about, on the typical source. So I just multiply by k. This becomes dimensionless. It's no longer a time. It's just a number. Okay, and so of course it's k times eta. So this is a function of k, and it is a function of eta. But in reality, it's just a function of the product. Okay. Okay. And then here, I mean, you can take whatever you want. In reality, you want it today, of course. But at some point, in any case, it stabilizes. Okay. Anything else? No? Okay, so now I wanted to give you an example of signals. Okay, so we already went through the different phase transitions that can lead to the production of gravitational waves. Of course, what you need to consider is that all this is really physics beyond the standard model. So these are just proposals of sources. Of course, they are based on what we think might go on in this phase for which the standard model is no longer valid because we haven't tested it. But there are serious proposals, and so here I'm just giving some detail about a few generation mechanisms, okay, of gravitational waves. So the first one is inflation. So as I told you, inflation is the phase transition of the inflaton field, okay, and in general, inflation is what is probed by the cosmic microwave background. So we have already seen these bounds here, okay, and basically what is the usual prediction of the usual theory of inflation, which is low roll and single field, is that this signal is, if you extend the theory up to very high frequencies, you have no hope to detect this with present neither future detectors. Okay, and that's because the actual spectral index of this signal is related, for those of you who know, to the first slow roll parameters, which is a small quantity. Okay, so the prediction of inflation is that this spectral index is small and negative. So you certainly don't hit the sensitivity of any of these observatories. But then what you hope, okay, here I have an explanation of this. So the tensor spectrum, okay, that comes out of the usual inflationary theory depends on the energy scale of inflation. This is the Hubble factor as inflation normalized to the Planck scale. And then this is K, so it is the wave number, okay, that tells you this particular behavior. And the prediction is that the spectral index is minus 2 epsilon, where epsilon is actually a parameter that is telling you how much the potential of the inflaton field is varying, okay? And because you want, during inflation, that the energy density in the universe is dominated by the inflaton field, okay, then this, and is dominated by the vacuum energy, this quantity must be small, okay? So basically, the gravitational wave signal today that you get from the initial spectrum times a transfer function as this nt characterized by this nt, which is very small. Okay, and then there are some things that we actually measure from the CMB, which is we have an upper bound on the amplitude of this quantity, which is exactly this green line here. Okay, and then the rest are details that you're probably not interested in. So now what is the point of inflation here? What we would like to do? The point is, okay, but this is the vanilla slow roll inflation, but what if we change the inflationary scenario and we add here an active source, okay, that can come, for example, from the presence of extra scalar fields during inflation, and this actually enhances the spectrum. So we go beyond this simple scenario, standard field scenario, that has been tested at CMB scales, but that actually was not tested at these very small scales at which the gravitational wave interferometers are sensitive, okay? And therefore, maybe we can actually increase the spectrum here. We have no observational bound. The observational bound is only here. And maybe we can cook up scenarios in which this is actually realized. Okay, so that's the entire business of model building in inflation to try to get a signal that is visible with gravitational wave detectors. And this is one example, okay, in which you see is the same figure as here, okay, and it is focused on the Lisa band. And you see that with this particular model in which you add the presence of gauge fields during inflation, you can actually get something that is visible. Okay? Another way of getting something that is visible during inflation is to exploit the fact that you might get very high scalar perturbations. Okay? And this is not at all natural. But people are very much interested into this lately, so you might have seen papers about it. So what people do is that they actually insert in this inflationary potential some little phase in which the potential is almost flat, okay? And this somehow enhances the scalar perturbation, and then you have the production of gravitational waves at second order in the curvature perturbation. So it is now the scalar component at second order that is actually sourcing the gravitational waves. And why is this interesting is because with exactly the same mechanism, people want also to form primordial black holes. Okay, so it's going to be a model of inflation or models of inflation in which you have two signals, a gravitational wave signal, and the production of primordial black holes. Of course, I'm not pretending that you know, I'm just flashing what, people are doing nowadays to give you a flavor of what is the research. This is, of course, complicated model building. But you see, in the case of LISA, for example, these kind of processes in which you source gravitational wave from the second order curvature perturbation, so second order scalar perturbation, can give extremely high signals in the LISA band, and at the same time it can give you primordial black holes in a mass range, you see, between 10 to the minus 15 and 10 to the minus 12 solar masses, in which there are no constraints. Okay, so these particular black holes can still be the totality of the dark matter. So these models are a bit baroque, but they could explain at the same time a very high signal in LISA and what is dark matter. So in that sense, they are interesting. And another signal that can be interesting from inflation is actually what happens at the end. Okay, so during the slow roll phase is what would give you this very flat potential I was showing, but we know that this slow roll phase must end. And when it ends with a phase of reheating in which the vacuum energy of the scalar field is converted into thermal energy. Okay, that you reheat the universe and you enter the radiation-dominated phase. This process of reheating can give you gravitational wave production, okay, and this has been calculated many, many years ago, and back then the signal was esteemed to be completely uninteresting. Why? Because it occurs in natural scenarios at very high frequency, okay, so you see here 10 to the 5 Earth, this is hybrid actually, so 10 to the 5, but even larger frequencies. But now the point is that we have a plethora of proposals of gravitational wave detectors at high frequency. Okay, and for now they have a very, very bad sensitivity, but one can hope that in the future this kind of proposals of detectors will become much better, and so could access, possibly, if it was there, this gravitational wave signal from reheating. Okay, this is an example of how one could use the signal from pulsar timing arrays. If you assume, okay, let's suppose the pulsar timing arrays have actually measured a signal from inflation. Can we infer the characteristics of this signal? And the answer is yes. Of course, I mean, it's a game that it's a bit, okay, somehow must be taken with a grain of salt, but you can apply this formula that I showed you before, in which this is the spectrum from inflation. Of course, you need this spectral index to be very, very big, so you need to violate the slow roll condition. But you see, you are into this ballpark from the PTA measurement, which is in some sense still allowed by CMB, if you relax the slow roll scenario. Okay, now I only have a few minutes, so I certainly cannot tell you about everything. Okay, maybe I just sketch a bit what can produce gravitational waves at a first order phase transition. Okay, so now we have seen this phase here. And now, before I told you, right, we expect within the standard model 2 phase transitions, the electroweak one at about 150 GeV, and the QCD one at about 150 MeV. Okay, so this we know they have taken place in the context of the standard model, but in the context of the standard model, we also know that they would not give rise to any gravitational wave signal because they are crossovers. A sizable or detectable gravitational wave generation requires a first-order phase transition. So what is a first-order phase transition? Is a phase transition in which the field, the potential of the field develops a new minimum, okay, that's the phase transition, so the fields goes from this vacuum at high temperature to the broken vacuum at low temperature, but developing a barrier. And so the field is tunneling across the barrier, either quantum tunneling or thermal tunneling, and in real space, so this is in field space, what happens driven by the effective potential, but in real space, this corresponds to the nucleation of vacuum bubbles, okay? And it is indeed this nucleation of bubbles, okay, that is the driving force of the gravitational wave production. Because you have then in the universe, you will, it's like boiling water, you will nucleate these bubbles, and very fast they will overlap and collide. And so this collision basically has many sources of tensor anisotropic stress, either really just from the gradients of the scalar fields or from the bulk motion that is created in the fluid by this collision process, or from the generation of electromagnetic fields due to the bulk motion in this driven by the bubble collision. So there are several processes that can give rise to gravitational waves from a first-order phase transition, and this is very much studied. Okay, and maybe I don't want to go too much into the detail, but maybe I can show you. Exactly, I will end with these 3 examples, and then that's it. Because this is really the main point about first-order phase transitions. Okay, now, suppose that we consider Earth-based interferometers. Okay, so they have a frequency range of detection that goes from 1 Hertz to about 10 to the 3 Hertz. And actually, with this range of detection, you can cut out a given range of temperatures or energy scales in the early universe to which these particular interferometers are sensitive. Okay? And for Earth-based interferometers, this goes from about 10 to the 6 GeV to 10 to the 10 GeV. Okay? So in this plot in which here you see the temperature at which the phase transition is occurring, and here you see how fast it develops, okay, you see that LVK is actually cutting out some portion of this parameter space that has already been probed, okay, and it's probing phase transition at this energy scale. And we do have a very interesting case for this, which is the Peccei-Quinn phase transition, as I told you already. Now, for pulsar timing arrays, the frequency band is much smaller, so much lower frequencies, which means that we get a much lower energy scale. And the energy scale that they can probe, pulsar timing arrays, corresponds to something between 1 MeV and 1 GeV. And this is indeed the QCD energy scale. Okay, so pulsar timing arrays are sensitive to possible gravitational wave production at the QCD energy scale, where we have the QCD phase transition. For LISA, now we are in the middle. Okay, LISA is sensitive around the millihertz, and this cuts out then this particular region of energy scale, which contains, you see, from 10 GeV to 10 to the 5 GeV, contains the electroweak symmetry breaking, which is at around 100 GeV. Okay, so LISA can probe the electroweak energy scale and beyond. So basically, this is a serendipity of these observatories that for completely disconnected reasons, they can actually probe very interesting epochs in the evolution of the universe, where we do expect phase transitions to have occurred. Okay, and I think I will stop here because it is already...
Thank you, Chiara. Yes, question?
You briefly mentioned about those very high frequency gravitational wave detectors. I was wondering if I need to hold my breath and think if they're gonna be built
right.
soon, or we don't need to think about that?
Yeah, so I would not focus a PhD thesis on this yet, in the sense that no, it is a very interesting physics, very interesting. But for now, the sensitivity range are much higher than you remember probably this morning I was showing the bounds, upper bounds from Big Bang nucleosynthesis and CMB, these integrated upper bounds. The sensitivity is sort of 10 order of magnitude worse than these bounds that we know are there. Okay, so we are very far yet from what we would need. I mean, we are very far from what this kind of interferometers can do. LVK, LISA, PTA, it's very far. But it is promising because, people are working on this, are developing the technology, and so sooner or later, one can hope that they will be operative.
Okay.
Just about the PQ phase transition, can you remind us why it's happening at these scales? Why do we think it's happening?
So, it is actually, right, so I think these are observational bounds, okay? So one point is that you actually, so the Nambu-Goldstone boson that corresponds to this phase transition is the axion. I'm sure you heard about it. And the axion is a stable particle that can constitute the dark matter. Okay? And if you don't want to have too much dark matter in the form of axions, you actually bound the scale of the phase transition.
But this is in the pre-inflationary or post-inflationary?
Post-inflationary.
Okay,
post-inflationary
scenario.
Yeah. And then the other bound also comes from observations. But now I don't recollect exactly from where. But this is observational, please.
I just want to make sure I understand the correspondence you're establishing here between the frequencies and the temperatures. So I understand that the temperature you're putting there for the phase transition is a proxy for time, right?
Yes.
You go further back in the universe,
Yes.
the temperature increases.
Exactly.
And that's also a proxy for scale, like the
Because
causal length, that sort of stuff. And is this the reason why?
Indeed. So if we go back to the fast case, okay, the temperature of the phase transition is actually determining corresponds more or less to this peak. Okay? So basically, and so here imagine that you superimpose, do I have a better plot for this? Maybe this one, yeah. So here you have omega as a function of frequency, and now let's focus on this particular parameter, which is the temperature at which the phase transition is operating. If you vary the temperature, you see you are varying the peak of the signal. And now this is compared to the LISA sensitivity, okay? We are here in the millihertz, okay? And so basically this is normalized to GeV. Here you go from something that is about 10 GeV to 10 to the 3 GeV, and then you exit the sensitivity.
Okay.
Now if you take the sensitivity of PTA, you go to the nanohertz, and correspondingly you need to change T star.
Okay, so LISA can see first order phase transitions, but not any of them has to be at the right temperature, so electric scale more or less.
So no, the point is that because you have the sensitivity, so you use the sensitivity range of your interferometers to infer which epochs you can probe, and you fall on epochs in the universe on which you have interesting phenomena. LISA gives you the electric epoch, and then you say, I can probe the electric phase transition. PTA gives you the QCT epoch, you see? So, yeah.
Thank you.
Any other question before we change epoch? Okay, thank you again, Chiara. So we can do a 5-minute break so that we can install the new presentation.
ci rifacciamo alla fine. Ci rifacciamo alla fine.
C'est vrai que le temps est très contraint.
Oui, mais c'est la partie pour certains numéristes qui, en fait,
Oui, te fait perdre un peu de temps. Ouais. Mais bon, c'était quand même intéressant. Donc.
c'était vraiment